So on this slide, we are giving a list of of networks coming from real-world measurements, which are showing power law distribution, and it's an impressive list. In fact, we are going to get back this later on. Okay, I'm just showing you this one for now. Instead, let's get back to the detection and visualization of power law networks. And what we can see on this figure is an interesting side effect, which is interesting in a sense that we would like to get rid of it. And is the following. So we have the log-log plot as before, and you can see here that in the tail part, so in the large K region, we have a mess, a kind of mess here, which is not really the thing we are looking for. Instead, we would like to see a much smoother picture, and on which the line fitting is shown in a better sense, a nicer sense. And we can get this by the so-called logarithmic binning. Okay, so it's visualizing more insights about the power lawness of the network, the degree distribution of the network. And so the binning is something like this, that instead of having 1k value for each and every column, we have a collection of k's. In the first column, we have k equal to 1, so the 2 is not included. Then in the second column is 2 and 3, 4 is not included. In the third column, then it's 4, 5, 6, 7, and then 8 is not included. And in general, we have this sequence that the k is between a to the power of n minus 1 included and a to the power of n excluded. And in this way we get much less noise in the tail of the histogram. But of course some details are going to be missing, so this is a kind of debate or some kind of price which you pay for this nice figure. So you lose some details. And okay, so here is some mathematics. It's very simple, so I just want to show you this one for the reason to see that mathematically we can see that the so-called CDF method, which stands for cumulative distribution function, is the following. So we have this capital PK, which is going to be the cumulative distribution of nodes, the number of nodes with degree equal to k or greater. So PK, capital PK, is going to be the probability that a randomly chosen vertex has degree k or greater than k. And so how can we calculate this one? Is that we have a running index, which is going to be k dash, and this k dash is running from k, so the chosen k, up to infinity, and then we are summing up the small pk dashes. Okay, now assuming that the degree distribution of p sub k follows, so I mean the small pk follows power law, then what we have for the capital PK is again power law. So I'm just replacing the PK, the small p sub k, with the formula which we used before. Okay, let me get back to the slide. So this one here. Okay, and I'm substituting here. I need to use k dash, or k dash, because now we have that running index. We have an approximation here which we can say that okay, now this is in fact it's a sum, but we can substitute it with an integral, which if you want is the continuous version of a discrete sum. So this is why it's an approximation. And why we are doing this, because for this kind of integral we have a closed formula, and that closed formula is k to the power of minus alpha minus 1 divided by alpha minus 1. So that's the closed formula, and then it's multiplied by capital C. And the conclusion, the very simple conclusion, is that if we have a degree distribution P sub k which follows power law, then the so-called cumulative distribution function, which we denoted by capital Pk, it also follows power law, but the exponent in that case is alpha minus 1. Why is it interesting? It's interesting only because I wanted to show you some formulas and the typical derivation of this kind of facts mathematically. So back to the log-log plot, but now for the capital Pk. Now you can see that in fact again we can fit here almost a straight line, which is definitely an indication, although not really a proof, of being power law. For directed networks, the CDF plots they look very similar, but now it's not only for the in degree, I mean the degree, then it splits, right, to in degree and out degree, and this is for, these two are corresponding to it. So I mean they are going together because they are for the World Wide Web, and this one here is a citation network, which you can see it also follows power law. I mean the cumulative distribution function of it. Now just as a recap, so it's very easy to calculate the degree distribution, because the only thing we need to do is that we have to make so we have to do the measurement of the degrees, and then rank accordingly the nodes in a decreasing order. So higher in the rank means larger degree, and if we do so, then we get this pk values, which are the rank divided by n. Okay, that was that's the meaning for the capital Pk, and then in the plot we are plotting the last column as a function of the first column, and that gives us the cumulative distribution function. Mathematically, it's not valid to just simply put a line there and then trying to find the slope of it, but instead we have like closed formulas for this kind of analysis, and you can see the book for the details, the book of Professor Newman for the details, and it turns out that alpha can be calculated by using this formula, and this sigma value here is the standard deviation in our statistics, which has also a closed formula. And as I mentioned, the internet network, which we were visualizing in the previous slides, for using this kind of alpha and sigma values, we get 2.11 for alpha and plus minus 0.01 for the standard deviation. So this means this definitely suggests that our value is statistically a good one or useful one, and as I mentioned, typically the alpha value in real world networks, they are between 2 and 3, and for this internet subgraph is 2.11.